continuing on from the examples that we've set up in 9.1, we're continuing to talk about compound inequalities. We arrived at the example of talking about set notation. We've been using set builder notation to describe solutions to compound inequalities. And we started getting into the symbols that we need to use when we have more than one interval that we need to show that either interval could be a solution. And the interval I believe that we had from last time was that we were going from negative infinity to negative 27/5, and we had to include it. And then we were saying we had to do the union of, and I'll get to what that means here in a second. And then our second interval went from 3 to positive infinity. Okay? So this comes to us from the early, or the late 19th century, early 20th century. I'm not going to get into all the history, but it's a very revolutionary way of thinking about numbers. We started thinking of them as sets, as collection of things. They represent collections of things. So, for example, and anytime that you'll come across a set in your textbook, it'll be a capital letter. So I'm going to let A be a set of numbers. 1, 3, 5, 7. Okay? So this represents the odd numbers that are between 1 and 8. Right? And this is how they're described. I could also say A is, using set builder notation, x, the set of all x such that x is a real number and x is odd and x is less than 8. Or I could say x is an integer. How about that? Or a whole number. Okay? This is the same kind of notation we've been using, but we're talking broadly about sets. This is a set. Okay? All intervals can be written as sets. Any groups of numbers can be written as sets. Even one number can be written as a set. So 1 can be written as the set of all x such that x equals 1. Okay? And I know this seems like a really silly example of using notation, but this gets really profound. We have this symbol called the null set. This is null set. It's also called the empty set. For those of you that go into computer science or computer programming, you'll get used to the word null. Probably some of you already are. So the null set is the empty set. It looks exactly, it's got nothing in it. Okay? So we actually, when we are solving compound inequalities, sometimes we get no solution, right? For example, if I were to ask you what value of x, when we take the absolute value of it, is going to be less than -1. What do we know about the absolute value function? Does the absolute value function ever spit out negative numbers? No, it doesn't. So can a positive number ever be less than a negative number? Right? Can a positive number ever be less than a negative number? No. No, it can't. So we say, well, we write no solution, and we put it in a box. Right? But mathematicians don't like this answer because it's in English. So they would say, what you want to do is you want to write the null set, the empty set, the set with no numbers. Okay? That's the answer. Because that's a thing. No solution is a void, and we don't like voids, and blah, blah, blah. All right. The other set, we also have a couple of other specific sets, but that's for another day. the main takeaway that I want you, so we have the null set, we have the union operator, and then we have this other operator, which means the intersection, or the intersect. This is the union, and this is the null set, or empty set. Okay? And you'll see these symbols a lot when we're dealing with inequalities. Not just compound inequalities, but also anytime that we have an inequality, we're going to have a range of numbers. And anytime we're talking about a range of numbers, we tend to talk about them in sets and intervals. Okay? So basically, the trick that I like to remember when I'm trying to describe this distinction between interval notation and set notation and the specific symbols that are in both camps, like union and intersect, is that if I were to write the word "and," I would have to start with an upside down union, and I would just draw something through it. So what intersect really represents is the idea of an "and." So if we're taking two intervals and we're saying the elements in those intervals that are in both intervals. For example, if I had the interval that went from negative infinity to 2, and I had the interval, and I wanted to say the intersection of that interval and let's say 0 to 5. The result of that are the numbers that are in this group and in this group, okay? So I would have to say all the numbers between 0, so let me write it on the number line, it's probably a good way to visualize it. The first interval starts at 2 and goes backwards, so from 2 to negative infinity, right? And I would have to exclude this one, wouldn't I? Because I'm using my parenthesis, not my bracket. And then the second interval, I would have to exclude 0 and go this way. Right, well, not all the way. I have to go to 5. And I would have to exclude 5. So let's say that's 5 and there. So when I'm using the intersection, I'm talking about the numbers that lie in both intervals. Not the ones, not like our OR inequality where they can be in either camp. They have to be in both in order for them to be a solution to this expression. So those numbers are the interval from 0 to 2, right? They're right in here, okay? Those are the only numbers that are in both sets, okay? Hopefully that's a good way to visualize what's going on. So, and we've been playing with union, and that is the same thing as OR, okay? So let's start working with some of these examples. Let's work a couple examples from the book. One will be an example where we are talking about two sets. And then the second is going to be more typical of the kind of homework problem or test problem that you'll be given. So let's say, let's use this, let's start with the set example. So I have a set of all x such that x is an integer. Okay? Integers are all the numbers from 0 to infinity that are whole numbers. So 0, 1, 2, 3, and nothing in between. No fractions, all right? So integers. And then I'm going to say B is the set of all x such that, oh, even better. Why don't I just give B okay. If you were to ask, or if I were to ask you to find this, what would you do? Right? Well, if you saw this on a test, like find A intersect B, there's a lot of mathies in there, all right? But we've talked about all the pieces that we need to do to solve this inequality or to re-describe this set intersection. So we would we'd start with your most restrictive set, which is 2, 3, 5, 7, and 11, right? And then you would want to know the ones that are, so another symbol that I'm going to use, and it might show up in your textbook, is this symbol, which means element. So what I'd say is X is an element of A, right? So what this is saying is X is one of the members in the set of A. So is 5 an element of A, right? Is 5 an element in the set of A? Well, is 5 an integer? Yes. Okay. Yes. Or we'd say true. All right, so that's an example of how we'll use that symbol, and that's how we use it in set theory. Okay. So finding the intersection of A and B, we have to find all X such that X is an element of A and, we can use the symbol, or we could probably best to write and as we're translating it. And what am I doing? I'm building set notation. X, it's the set of all X such that X is an element of A and X is an element of B. If you were to write this in set builder notation and leave it as a solution, you would be 100% correct. Your instructor would have to accept this as an answer. And if he didn't, you would tell him that his axiomatic set theory is way off, okay? And he would probably fail you just for being, so don't do that, but you could. Another way to write this is to look at the constraints of the set. So the smallest set that we have is B, right? It has 1, 2, 3, 4, 5 numbers in it. The set of A in it has infinitely many integers in it, right? We haven't stopped counting integers, and we're not likely to. We get really tired of doing it, so we let computers do it. So really, the solution of the intersection, right? If I were to write it as a set, it is just all these numbers, right? All those numbers are in B, and they're all integers. So the solution set would be 2, 3, 5, 7, 11. Okay? So that's a little preview of the kind of things that you'll be doing. And they'll be a little bit more difficult for you. If you go into set theory, it'll get a lot hairier. But it's nice to get comfortable with the terms. Okay? The second example is going to be like the examples that you get. Okay? And it's going to be like it because I'm borrowing it from the textbook. So let's see. We're going to solve an OR inequality. I believe it's less than, yep, or, yeah. Okay. So like we discussed in the previous video, we're going to, because we have an OR inequality, we can't rewrite it as a compound inequality. So we'll just have to take each piece, put it on the number line, and then find out how to rewrite what our answer is in either set builder notation or interval notation. Okay? So the first piece, we treat it like an equality, and what we want to do is we want to isolate x. So in order to do that, we add 5 to both sides, and we get negative 2x is less than negative 3 plus 5 is going to give me a positive 2. Dividing by 2 on both sides, I get, well, let me divide by negative 2. When I divide by negative 2, and I'm dealing with an inequality, I have to flip the sign, okay? Every time that you're dividing by a negative, you flip the sign of your equality. And that's a whole nother video. I'm not going to get into it right now. But finally, I get x is greater than negative 1, okay? And then, let's see. I'm keeping my or. Now I'm solving this one. Well, I'm going to divide both sides by 6 to get x all by itself. 0 divided by any number except 0 is 0. Okay? So I have my two solutions. Now let me go to the next step, plot both solutions on the number line. Let's see. Write my 0. X is greater than -1, so I'm going to plot -1. And because I don't have my greater than or equal, I just have my greater than, I have to exclude my 1. Okay? But all the numbers, X is on the loud side, he's bigger than. So all the numbers that are bigger than -1. Okay? And now just for illustrative purposes, I'll write a second number line to describe my solutions that exist here. So X is less than, not less than or equal to, less than 0. So we have to exclude 0. And then all the numbers that are less than that are the negative numbers. Okay? So now, looking at my number lines, I don't have a gap like I had in my example from the last video. I have overlap. So if a number satisfies this condition or it satisfies this condition, then the way that I would write this is all of my numbers satisfy either one of those conditions, right? The numbers that go from -infinity to +infinity. Because the numbers that go from -1 to infinity satisfy this part, and the numbers that satisfy 0 and lower satisfy the second part. And there's no gap between both of them, they overlap. So we don't double count those because we don't double count solutions in math. We just say that all real numbers. So if we were writing our solution, we would say it is the set of all x such that x is a real number. If we were writing it in interval notation, we would say x goes from, and because we're dealing with infinity, we exclude it, but x goes from -infinity all the way up to +infinity. It includes everything. Okay? Hopefully that was a good example for you of working with compound inequalities, both the and the or, and also an introduction to interval notation and set builder notation. These kinds of notations are going to be used all the time in higher level math. So it's good that you get used to them now. All right?